Okay, let's talk about our bridge.
Okay, I'm
You
going
want to advance this?
Yeah, I'm
Okay.
going to take you through this and the details. And when I was hired to do this, I always look for a metaphor. I look for clues in the environment. I look for man-made forms and natural forms. Well, Mount Hood is spectacular to me and to most of you, I'm sure. And it's white most of the year. So I felt that the angles of the slopes of that, which are important. Don't tell me this thing's gone out on us. Yeah.
Okay.
You know, what's important is if you look at the slope on the right side in particular, you'll find that it's the same angle as the cables on the bridge. The cables are white, so they tie into that Mount Hood. And so that's what's important. And let's see if this thing is working. No, this thing is dead. Maybe something.
Oh, it is. Well, I guess we'll have to do, somebody will have to man the,
Yeah, she's going to hit something. You know, I'll just continue. But with that
Here,
form, what happened was that the tower, by the engineers, they lowered the height of the tower. And in doing that, it made it so that we as the architects or designers, we could make it and mimic it the same as Mount Hood. So the angle of the top cable sort of matches the hood. Now, we used the rule of thirds on this as well. Let me see if this thing works now. No.
yeah, I think that's not functioning.
Okay, so what
So
happens
she'll
is
slide.
I put the Mount Hood there so you can see how it matches up very nicely with the bridge. And I think that's so important because on a nice day like today, we could see Mount Hood. And when you're on the bridge looking through the cables that are white, it really ties itself together. So the next one. And here's where I use the rule of thirds. And to explain it to the layman how we use it, this is a regular photograph that some photographer took, but you can see the lines on there. And when you work with engineers and you explain this process, it's all mathematical. And I use the golden means, the golden section, the golden triangle. They understand it, and you can transfer it into mathematics. You don't say it sort of looks good and you can't explain it. So it's all related to that. But this shows you how your bridge is 1/3, 2/3. And on this particular section, you can see how the wind fairings, that's the element. Okay, great. Thanks a lot. You can see how that okay, you have the 1/3, 2/3 business. We have this wind fairing. We've got open railings, so the wind, when it was wind tested, Simone was saying we could get up to 150 miles an hour and it's still stable. And we extended this down because we wanted this to match the chevron side of this leg section, this part. So it's all this vocabulary I was talking about earlier, it's all tied together. Now this is another important feature. If you look at the top of the tower and the top, I use the top of the trees as like the feather line to shape the towers. This goes through the handrails. It's also, you know, picks up the local scene, so that's why that's up there. And then this shows you how we pulled the deck off the tower leg. And the idea is we wanted the tower leg to read through. So when you light it at night, it also lets light through there. And so in the daylight, if you had seen it today, you'd see how the shadows come through. And you really can see how the tower legs works in the structure. But again, we used the chevron form everywhere we could. And this works for wind, but it also works for the current of the river. And so it has a real meaning for this site. And this shows you just when they're forming the tower leg, and I got to give David Goodyear a lot of credit because he managed to work the forming system on that tower leg, which is really difficult because usually you go straight up or taper it in one direction. But this one, we did it in all directions. He pulled it off within the budget, which was incredible from our point of view. And you can see how we took the chevron and the pentagon form here. We put it in even these pilot elements for the boats, and it's even in the handrails. So here again, you can see we opened, this is a barrier that was developed in California. It's called a T80. It's been crash tested, but I wanted to open the voids, and this void picks up the same dimension that's on the handrail. So you go across this bridge, and there's this rhythm that develops as you cross it. Instead of this being a solid barrier that's on most of your modern bridges, it's open and it lets light through, and it helps you see the view that's underneath it. This shows you the handrail, how the handrail top ties in with the tower top, and how so it's all the same vocabulary. And then this also shows you this wind fairing. And what's nice about this, it enhances the underside of the bridge, and this is the tie-off for the cable that David Goodyear produced in his group, and Simone was part of it as well. So here you can see how we brought this all together, and even in the details of the elements, you can't really see it on this one, but let me go back. But here, we even in the posts that hold the lights, we took the same shape of the towers. If you get out there, you'll see also the supports that are on the catenaries that take the cable. So everything was tied together with the chevron form, and it was related to what's in this particular area.
Real quick before you switch the slide,
Sure.
what about the box?
These boxes.
Yeah.
Where's David? Another David. No, that's something we tried to push it underneath, and we tried to shorten it and make it smaller, but it couldn't happen. So that was one of the.
Because I always wonder about that. It's like
Yeah.
you see all this beautiful detailing, and
Yeah,
then,
right.
then
Yeah.
the electrical box is sitting
Yeah. No, I mean,
like this uninvited guest.
we
you
got
know?
it equal on it. Well, there's one on either side of the main center.
You need to,
But it's been a problem, I'll tell you. You shouldn't pick that one out.
you got the complication of running a train on the bridge, that's the reason.
Yeah, but they
Yeah.
can't do a better box. We can't get the chevron in.
No, we tried to make it smaller. We'd go down to the height of the auto barrier, the vehicle barrier, and we couldn't make it that small. We tried to, in some cases they managed to put it on its side, but that's one of the problems we had, yeah. Not a problem, that was the way it ended up. And then this again is one I've just showed you. And we used a horizontal rail in here because it doesn't wreck the view so much. When you use vertical rails, they stack up. So to go horizontal it opens the view up. So when you go on this bridge, what's interesting is when you're standing and you look down, there's a slight tension in that. And good art usually has tension points. If you can think of Michelangelo in the ceiling, the Sistine Chapel where because Moses is touching, and they don't really touch, and it sort of creates that point. So there's that element in it, but it's very subtle and it might not be that important to anybody else. Okay, that was a quick run through. I was told to do it quickly.
Okay. Simone, you want to talk about it?
Sure. I would talk a little bit about the challenges that were in my court. We were selected by TriMet for a bridge type study in April of 2008. So I'm actually been with this bridge now for exactly seven years. And the bridge type selection was a fast process, very challenging. We were reporting, me and an architect were reporting to a selection committee every month. We started with 22 bridge types, everything in existence, suspension, cable stayed, arch, extrados, even 2 or 3 movable options. And then we narrowed it down, and when we narrowed it down, it was down to just several bridges, and cable stayed was one of them. But I had difficulty actually with the selection committee with the cable stayed bridge because first several options I came up with had fairly massive towers, tall towers, which are needed for a cable stayed bridge for it to be effective. And at some point in time, selection committee put a limitation on the tower height at 180 feet. And the reason for this limitation is that the tower will never overshadow the tallest building in downtown. Now, to resolve this issue, to have a bridge with this kind of a super short tower, it's probably one of the shortest cable tower for any cable stayed bridges ever built, we came up with a system to run the cables through it called saddles. And it's the first in the United States application of saddles, of commercially available saddles. There were 2 other cable stayed bridges built with saddles, and they've designed and built one of them, the Pascal Canwig. But this bridge has the first commercially produced saddles. And what it allowed a short tower, only 180 feet from the water, very compact in a cross-section, and solid. Absolute majority of the cable stayed bridges have hollow tower because the cables are stressed from inside of it, and that makes the tower very massive looking, that aesthetically would be unaffordable for this bridge.
So explain what a settle is.
Saddle is a steel tube, and do you have a picture of it? Because it's again one of the slides I sent to you. It's a steel tube that is embedded. Well, you can kind of see it on. If you look at the tower, you can barely see it. It's like a round dot in the tower. It's a steel tube through which the strands of the stay cable go through. What you're looking at the picture, you see the pipe for the stay cable, which is a HDPE material, and inside it is the steel strand. So the steel strand goes through the tube and through the saddle, comes to the other side, and it's stressed from the deck, which is, I can't say it's totally unusual, but it's fairly rare for cable-stayed bridges to be stressed on both sides of the stay cable at the deck level. Most of them are stressed at the tower, which is more convenient and less expensive.
I think just to go further from, what they're saying is when you do most cable-stayed bridges, they're hollow. And the reason they're hollow is they want to inspect the end of the cable, so they put elevators and stairways in it. And this bridge, which was great for us, to make it really slender, and Simone worked with this idea, and the engineers have a hard time with this sometimes because the saddle itself produces a moment in the tower. It's like a rocker. And so they got to tie the base of it. So it's new, but it's really interesting because they were able to pull it off here.
Simone, is this like a breakthrough? I mean, will we see other shorter cable-stayed bridges, or is it a kind of one-off? And do you think?
Well, to me, it's one-off, and they feel free to correct me. But to me, it's one-off because, again, going back to the bridge type study time, one of the bridge types we developed kind of at the level of rendering was the so-called extrados bridge. Extrados bridges have the shortest possible tower of any cable-supported bridges, but they have much more massive superstructure, and that would, and they typically at least a quarter, 25% or 30% more expensive than cable-stayed bridges. So we would not be able to afford it cost-wise, and aesthetically, neither the selection committee nor TriMet liked it. So making it the bridge that actually was designed at 180 feet, it's just barely above the extrados type. Yet it is technically it is a cable-stayed bridge, and that allowed this to be built at very, very reasonable cost, actually below the budget that TriMet got.
Yeah, if you go back to the previous slide, so if, first of all, Donald was nice to give me credit for the tower, but the construction was done by Kiewit. This is not the first job I've done with Kiewit, and they have an awful lot of very talented people that do a fabulous job, so lucky to work with them. But if you look at I guess you can't see it here, do we have a slide that shows the profile, that shows the depth of the bridge? One more. Isn't there a?
No, I think
that's
the next
it.
one is looking at the
Or you
underside.
could
All right,
go back
so
to that section.
go
I
back to
showed.
that. So
Yeah, the section, yeah. Keep going. One, yeah, that one. Maybe talk about
yeah,
that.
so the depth,
Maybe
it's a little bit
pointer?
tough with this one, but what Semyon is talking about, actually go forward to the shore shot from the river.
The underside, I guess.
There. Whoop. All right. So if you can see how the soffit of the bridge dips down at the tower. And what Semyon is mentioning is if that was a typical extrados where the tower would be maybe 20% lower, 25% lower than what it is, that depth would be at least twice what it is.
Yep.
And if you go to I'll call it a pure cable-stayed bridge, where the tower was 25% taller perhaps, then the soffit would be parallel. You wouldn't have that dip at the deck. So this is very much, it is fairly unique. It's in between, while, if it were a design build without the architectural constraint, you probably, for future jobs, you would not see these proportions necessarily, but it is beautiful. I mean, it fits right in the middle. Donald and Semyon did an excellent job of laying this out in the context here. It did make it quite a bit more challenging to design because those two extremes, the pure cable-stayed and the extrados, both have a more analytical foundation to them. So this was kind of cutting new territory on the design side as well. I don't know, do you have a view of the midspan? Did you ever put that slide in?
I
There's a slide of the,
It's not there.
I don't know if you want
Yeah,
to bounce
well, I'll
around.
talk
or
a little
let-
bit.
Yeah,
Yeah,
we'll
Oh, sorry,
get to that later. Go ahead.
No, we try to use the underside of a bridge like this, like you're looking at a ceiling of a cathedral. And if you've been to Europe and you see the Gothic churches like Notre Dame, things like that, you'll see that the underside is really important because we look at it 360 degrees. In an airplane, on the bridge, on the river, cyclists. And so it's really important this underside we hit as many pipes as we could, so it's a very clean element. But also we shape the cross beams. We've given them some massing on either side, which works structurally, but in general, design built, they just go straight across. But there we were able to shape it and get everything in that center piece, that all the conduits for the electrical. So it's important that the underside has as much attention as the top, and if you have good engineers like the two I've been working with, it's achievable, but it does take a lot more effort. The electrical work on this was tough. There's a lot of things about it that were, everybody worked hard, and Kiewit, of course, came to the bat and really helped everybody make it a super bridge.
David, did you have something else to add?
Later slides. I think these are Donald's too.
Yeah, I thought, well, anyway.
Yeah.
Is there another slide that illustrates the point?
You didn't put that elevation view of the midspan in there?
No, I don't think I
Did I
got
send
it.
No, I
you? No.
saw
It probably
The
came
one-
came the same time.
They
Okay.
disappeared with mine, or
It
they
disappeared with
looking for
yours?
my slides?
Maybe the same problem I had
Is
with
that that's the last slide, the profile?
Yeah.
Okay. So if you go back a little bit, we can't really see it, but out when you walk the bridge out there, when you look at the underside of the bridge, you'll see the cable anchors that Donald mentioned are for 2/3 of the bridge, and then the middle third of the bridge, the cable anchors disappear, and the cables come down, and you'll see it very readily when you go out there and look. One of the constraints that kind of popped up on us in the design build phase was that we had to get the navigation clearance underneath the bridge right in the middle part of the bridge. And so if those cable pots came down, the cable anchors came down, we would encroach on that envelope. So we actually developed out of necessity, we split the edge girder. Again, you can see it from looking down at the shore. We split what was a solid edge girder into pieces and hid the anchorage in between those two pieces. It was certainly more expensive to do that, but it ended up actually looking quite nice. And there are some technical benefits actually of doing that in terms of thermal controls and things. So the next bridge I designed, which unfortunately we just lost in a competition last week, but we split those on purpose and did the entire bridge that way. because
So
it
this is
did
kind of
have
a
the
late
benefits.
game save then?
Yeah, this was a late game deal. This was after we won the job. He said, "Uh-oh, we have to fit the ship through there." And so, but it ended up. Yeah, I'm really happy with the way it came out. It came out very nice.
Oh, it came out really well from
Yeah.
an architectural point of view, too.
You did the split girder for Corpus Christi?